Okay, so what we'll do today is we'll change the course a bit. We'll now whole first half of the course, we essentially only talked about neutrino oscillations. We say they have mass, they mix, and therefore we get all these features that is found in the experiments with solar neutrinos, atmospheric neutrinos, and accelerator neutrinos. So what we will do for the next 3 weeks is try to see what this means from the theory point of view. So of course it's very simple to say that things happen because neutrinos have mass. But neutrinos happen to be a part of one standard model. So it's essential that they fit in the framework of standard model. And therefore one cannot randomly say that I need neutrinos, therefore I need masses for neutrinos, so I just use it masses. They have to somehow conform with our bigger picture. So what we will try to do today is we will try to look at standard model. I think most of you have done at least one particle theory. So I suspect that everything that is done today, because I will not talk about neutrino masses, I will talk about masses given to other particles. Because then tomorrow onwards we appreciate why it is difficult to give masses to what the problem. Okay, so today we will just see how to give masses to other particles. Okay, so before that, what I do is I simply introduce, remind you of the standard model, okay, how exactly it is constructed, and how to write down the interactions. Okay, this will make us appreciate, think of more ways of giving masses to neutrinos. So what we do is the following. So first I'll remind you of this standard model diagram here. So all of you have seen it in some form or the other. There are many ways of writing it, and I will show you my form, which is the thing I use, compact notation. And then we will go and talk about mass of the standard model. So standard model will have mass terms for all the blocks. There will be mass terms for M1, V1, and tau. There will be mass terms for W and Z. But neutrinos will remain massless and photons will remain. So at the end of today's class, this is where we should reach. See each particle getting mass and each one. Then we see highly low. So let me remind you of this diagram. So have you seen the diagram in this form earlier? If I show you something like this, can you recognize what it terms are? So let's go. Okay. So what are the first two terms? W and D. So I am not seeing recognition of many cases. Okay. So the W term, okay, so standard model. So this is not a complete standard model. So in the electronic part of it, the standard model is SU3 cross SU2 cross U1. Standard model is SU3 color cross SU2 left cross U1 language. What we will talk about today basically is, because we are going to deal with neutrinos. Here there won't be any color forces, so it's okay to neglect this. Yes, we'll talk about SU2 cross U. We'll go through each of these things in detail. I just want to have a look at this pregnancy. So before we go to these, okay, let's go to these L's and R's. So standard model has left-handed fields and right-handed fields. So for example, if you think about clocks, so we have uptime clock and downtime. And in fact, they form a SU2 doublet. But then you have right-handed uptime clock and right-handed downtime clock. They don't form a doublet, they are separate. Similarly, we are going to have left-handed neutrino, that's electron neutrino, and left-handed electron. They will form a doublet, and we will have a right-handed electron, which will be a single. The standard model, as it stands, strictly speaking, will not have a right-handed. We will have this. These particles, so this and this, will be called as A, because of left hand. And these particles collectively will be called as. So therefore, when you go to this page, when you see L and R, L collectively stands for all these particles. So what does this mean? This means there are up and down type quarks plus neutrino electron pair. Up and down quark actually come in 3 colors. So although I written them only once, they actually are 3 copies of them. Plus all of this becomes generation, and there are 3 generations. So when I say L, L actually stands for, let's see, so 3 colors of quarks plus 1, so 4 doublets per generation times 3 generations, so 12 doublets. So L actually stand for 12 doublets of fertilizers. These are all left-handed fertilizers, so therefore effectively there are 2 components. And then we have got the right-handed particles. So again, up and down type quarks will appear with 3 colors. So although it looks like 2, they are actually 6. Plus electron, that's 7. Each generation is going to have 7 right-handed particles times 3 generations. So right-handed particles are, when I say R, I am talking about 21. Therefore, when I write things here, I am writing short form where L is some 12 doublets or 24 formulas actually, and this R stands for 21. Then we have this field phi, which is a Higgs. So these are formulas. Higgs is a scalar. For the Higgs is again a doublet. So if I want to write phi, is a doublet which consists of a charge, scalar, and a neutral. Phi plus and phi. These 2 are complex ones. You are here forward. Forming a doublet means that under SU2 they transform in circle. So I will come next 2 years. I will come and tell you how they transform. And the definition is doublets are those which transform in the same way under SU2. The way UR and DR transform are very, very different. So in fact UR and DR do not transform at all under SU2. So we will come to that. So let's see what else is. So now we know what are L's, what are R's, and what are Phi's. That was the standard. Now there are these W's and B's. Now, just like electromagnetism, it's also U1 gauge theory. So for any gauge theory, there will be a gauge boson. Gauge boson is mediate these forces. Yeah, so therefore, corresponding to each gauge, there will be one or more of these particles. P is that gauge particle which corresponds to this U1Y, which U1 Dighe. So again, we come to how it comes. This is just introduction to other parts. So P is the gauge particle corresponding to the Dighe hypercharge. And W is, you can see W is written as a vector. So these are the three particles, W1, W2, W3. They form three components of a vector. And these three are edge particles or SU2. So again, concretely what it means, we will see. But essentially we have got a weak hypercharge, which carries the force, whose force is carried by this edge boson called B. And we have got this SU2 well, which is the weak isospin. And that force is carried by these three particles called W1, W2, W3. What is it? Tau acts on a Pauli matrices. They are generators of SU2, and therefore we have here. So then we see all the terms. Then there were these terms, WPU, WPU, or PBU. So these terms are analogous to FPU, FPU terms that we see if we look at the Lagrangian electromagnetic. So many things can be understood by analogy in electromagnetism. Again, you have got, in addition to coupling with the photon, photon itself has a kinetic term, which is given by FPU times A. FPU is this, FPU is this. For electromagnetism, we have something very similar. Electromagnetism is also U1, sometimes called U1 of Q. And there you must have come across an object called as UU, which was WAU. And if you want to write the kinetic term in Lagrangian, it will be minus 1/4 of. So Lagrangian usually has three kinds of terms. It has terms which is, this is the kinetic term. So kinetic term for gauge field. So here gauge field is A. Plus, there will be kinetic term for fermion, which will be we want psi bar tenuous. So in fact we come with psi bar double, not tenuous. So this term is the kinetic term for the fermion. And plus, here is the interaction, okay, which tells you how fermions and this kinetic term. So then this is going to have something which is like psi bar, gamma mu, AU psi. There is a coupling constant. Let me confirm notation. So that's minus charge. So in photon, that's what you have. So this Q is plus Q minus Q. So this is the interaction. And also this diagram is given. Then you can use your Euler's Analytic Term motion, and they will tell you how things. And normally, what things that you will get will be direct equation. Look at this term, and we use Euler's Analytic equation of motion. You will get direct equation. If you look at this, and if you try to do the same thing, you get algorithm. Okay, because photons satisfy algorithm with tensor. are going to be interaction. So these terms B into B into are the kinetic terms of the B variables. I will tell you what they are. And W to the W mu terms are similar kinetic terms for the 3 W variables. So this actually includes 3 terms. This dot actually shouldn't be there. Let's go to the this dot is equal to vectors, which dot product means 3 different terms. Those 3 will be for approximately W1 W2 and W. All these terms give the interaction. Okay, so for example, if you look at this L bar, gamma mu, E mu, Y, L kind of term, this will correspond to an interaction. So let's write down this. So let's start this. R bar, gamma mu, G prime by 2, D mu, Y, R. Let's see what it is. So interaction term. So R bar, then I add gamma mu, then I add minus G prime by 2, D, Y, R. So Y here is hypercharge. YR means hypercharge of R. Okay. So let's say the values of Y. So we can combine that with G primes. And this means that we have a vertex. So this is R coming in, R going out, and this B. And the strength of this vertex is G prime Y by 2 times gamma. Okay. And presumably, given the strength of this vertex, you will at least know how to start calculating the cross section. But that's how it goes. Like actually, you look at a term. Interaction term normally has 3 fields in it. So you notice that all interaction terms will have 3 fields. For example, this is going to have L bar, W, and L. This term is going to have L bar, E, and L. This is R bar, E, and R. This will have, see, this is it is slightly complicated. So we'll come to that. So that takes care of all these terms. And for the last line, I have some more terms. These are interaction terms that combine left, right, and against. These will be terms which are so-called Yukawa terms. We'll come to them also. So we'll go to these levels. So note that if I forget about this last terms, so we'll look at the top part. Then the L terms and R terms do not mix at all. So you can consider this top part as something that gives me a theory for all the left-hand functions, something else for all right-hand functions, and they don't affect each other. Okay, they could be very different. So that's why without these masses, and what it is often called as a chiral theory, is that the way left-handed things function and the way right-hand things function are very, very different. It is only because we have got this final term, this Yukawa interactions, that left and right things leads to.
In terms of the diagrams, A has a vertex with B. R also has a vertex with B.
Yes.
So you can have that.
Yes, but not L, R, and B.
You can have
So L, R, vertex B is L, L, B. You can have vertex. So this is okay. So you can have L,
and then go to R.
B. This is okay. Yes, this possible. So you can have this going on. That's possible. I don't have direct AR. So what we do for next 15-20 minutes is go through these terms and see how these terms come out from them. So first thing we'll do is we'll only look at a situation where we have only fermions. Okay. There are no interactions. So the free fermions, okay, free fermion and free Higgs. And we know that when we have only free particles, the only thing we get is the kinetic terms. Right? So there are no interactions. When that happens, standard model looks very, very simple. Okay. So this is the way you start looking at it. So what I've done is I just blanked out everything that we did. So what do we have? So this term is L bar gamma mu I del mu L, which is the kinetic term for the alternate parts. R bar gamma mu del mu R, that's alternate components. For the Higgs, it looks like del mu phi mod square minus V of phi. V is potential. Okay. Potential is a part of the current, and I kept it there. So this is just like what happens, what is the Lagrangian for a boson. Del mu phi is equal to. Let's look at kinetic terms. So for fermions, we had something like L bar mu R L. For Higgs, we had I phi mod square minus E. So this is exactly what the real right is. I'm going slowly because I want everyone to be very familiar. Suddenly tomorrow we will start using all these notations much faster. So right now let's not talk about analytic terms on the gauge programs, we'll introduce them slowly. This is what we have currently. So this part all of it. Now we want to introduce the gauge interactions one by one. So first thing I will do is I want to introduce gauge interaction U and Y. What does it mean, introducing of a gauge interaction or a gauge symmetry? It means that I say that under certain transformation, my theory is going to be invariant. Which means that if I apply certain transformation, my Lagrangian will not change. So Lagrangian defines my theory. U1 is a special way of saying this. U1 means that if I change the phase of a wave function by a certain phase factor, my Lagrangian will not change. So formally speaking, this is what we do. So when you look at the first line, so you want to say that if I have a wave function psi, which is a field in my theory, I can multiply that by a phase factor which are parameterized like this. So there is e to the power I, g prime by 2 is a coupling constant, alpha x is a function of x, so it can be different at every point in space time. So local, so it's independent. And y is the hypercharge. So strictly speaking, y is an operator, and y acts on the field and gives some load. So whereas a hypercharge of let's say electron is -1. This means that y acting on electron gives you minus electron. So y acting on E will give you minus of E, as in the wave function. Y acting on psi E. Yeah. Right. Okay, so let's have this D hypercharge. So this idea is an operator. So y it acts on some psi and gives you something. Okay. As you know, quantum mechanics, it's not always true that this will give you some number times psi. It happens only when psi is an eigenvalue. Sorry, eigenstate. All the particles in Tata model are eigenfunctions of phi. So then we are saying one of the ways of saying that Lagrangian is over invariant also implies that your particles are somehow eigenstates also. So psi, all our psi's are going to be eigenstates of phi. However,
This how we are defining the particles.
no. Particles exist the way they are. I tell you what their property. Okay, so I tell you, see, the way I define y of a particle is by telling you what the values of it, what the eigenvalues are. Particles are what particles. In addition, I am telling you now that they are transform in a certain way under this symmetrical U1. And that's what I am going to tell you, how they transform. So how do they transform? So let's say I have an electron, so let's say psi electron will go to e to the power some I g prime by, this is a multiplying constant, so you don't care about this, g prime by 2 times alpha x, and let's say so I need a hypergenes. This is the way I need my electron transfer. The y of electron is, let's say, minus 1. Okay, En. Y of En is minus 1. Y of Er happens to be minus 2. So what does it mean? If I apply a transformation, if my psi e goes like this, okay, so psi e y is equal to minus 1, so my psi e will go like e power minus I g prime by 2 alpha x times e. At the same time, my psi er should go to e power minus I g prime by 2 alpha x times 2 So remember, the gauge freedom is freedom at all points in space, which is okay. But once you decide what this function alpha x is, this function alpha x should be identical for all the particles. So therefore, once I give you what y of the particle is, you should know how it transforms. So it's not like I transform electron the way I want and muon the way I want and u the way I want. That's not possible. Okay, so this should be very clear. So gauge freedom, although it looks like a freedom, it is a freedom, okay, but it is a very constant freedom. U1 gauge means once you have this function alpha x all over the space, this function is the same for electron, neutrino, uptype, or downtype, or Higgs, whatever. Okay, so alpha is not different from different particles. Okay, so that is fixed.
Here it is local.
Alpha is
Local.
so for every x, alpha can be different. But once alpha is fixed for some x, at that x, it is the same for all particles. That is it. Now, you have seen this before. So wherever I have y, for example, just put q, electric charge. Okay, and exactly the same thing will follow for electromagnetism. So if I use q here, so electromagnetism, okay, you will electromagnetism, it's a familiar thing. In that case, our psi goes to e power I g prime by 2 is e, yes, the electron charge, then we have got alpha x times q of psi. So what does this mean in electromagnetism? It means that if electron q is equal to -1, okay, then an electron, so psi of electron will go to e to the power minus I e alpha x psi of electron. Whereas if I want to calculate psi of positron, this will be e power plus I e alpha x psi of. Okay. So again, the phase transformations of electron and positron are going to be correlated because of Q. Q determines everything. And we saw in electromagnetism that if I only use this transformation, then my Lagrangian is not invariant. If I simply want to say look at this transformation, and if I look at the kinetic term, which is so if I look at this transformation, and if I look at my kinetic term, which looks like psi bar in psi bar gamma mu I psi. If I use this, it is not invariant. And we also have a trick we have to use to make it invariant. So firstly we say that the kinetic term cannot be this term cannot be kinetic because it is not invariant. So what we need to do therefore is my L kinetic needs to be something different. It should look something like psi bar gamma mu I d mu times psi. And we know what this d mu looks like. So this d mu is del mu rotation minus e times del mu minus in this case e times. This was the case later. Okay, but all I have done is replace this e by g prime by 2. Sorry. Wrong. So d mu del mu plus I e b times plus I e, and then we have got a mu times q, which is usually you say that for electron which is minus I e mu, for positron is plus I. That's exactly what you want to say. So this q takes care of charge of the particle. So d mu therefore should transform like this. But this a mu should also be transforming under the case of summation. And this a mu should transform like a mu minus e times delta. So what this means is that my Lagrangian is invariant under this case transformation, this phase change. If I change my kinetic term like this and my A transforms. So in this sense, if I satisfy 1, 2 and 3 simultaneously, then I get a consistent. So therefore when I say that my Lagrangian is U1 invariant, it means that my Lagrangian satisfies these three things. If it satisfies 1 and 2, the initial requirement is automatically satisfied. So this involves 1, you have to go from a simple partial derivative to a covariant derivative. This is also sometimes that's one. And secondly, you have to introduce a quantity which is called as B mu, which is the gauge boson that mediate. So if you want to have this gauge symmetry, you have to introduce an extra gauge boson, this auxiliary. That's the requirement, only one thing. Change of derivative and introduction of a gauge. That is the strongest. So here I have listed all the y eigenvalues of all the particles that we have. So what do we have? We have these neutrino electron left-handed, its common doublet, for which y is equal to -1. For right-handed electron it is -2. For up-down left-handed doublet it's 1/3. Right-handed UR is 4/3. DR is -2/3, and for Higgs is 1. So what it means is, if I tell you by transformation of an electron under let's say left-handed electron under this pivot Y, it means I already told you how Higgs transformed under this. Okay, all changes is that factor. So all this transform. This just tells you the proportionality. If this transform like this, the phase changes by some phi. Phase of ER will change by 2 times phi. And the phase of phi will change by minus. So this is how you introduce the gauge. Now there are 2 more important things that happen when you put this gauge. Firstly, this gauge goes on, cannot have a mass. And the reason is the following. What is the mass term? So see, mass is that term that appears in the Klein-Gordon equation. This is how particles are seen. This is the Klein-Gordon equation. This will come from a Lagrangian. That is something like this. LUB star LUB minus L square. Let's take real field. M square B square. L is equal to. We just factor of half, so factor of half, right? Factor of half in front of common. So the mass of this particle, therefore, is what appears in front of B square, which is true in general. For bosons, the mass term will always appear as minus m square times b square. Or if you want to write terms of b, take care of it. Derive it this way, that m square times b. But it's basically a term which is quadratic in the field. So now what happens? If we want this gauge goes out to a mass, then this term should be gauge invariant. So which means that if I apply gauge transformation, then this term should not change. I know how to apply gauge transformation. I know what happens to dV. So we looked at what happens to dV. dV goes to dV minus g by 2 times dV. So that goes to minus m square. Goes to dV minus 2 delta. Is dV also dV minus g by 2. So clearly there is no cancellation, and therefore this term does not remain gauge invariant under gauge transformation. So under this, see, gauge transformation should not change our results. Right? So therefore, if you are changing a Lagrangian, there is some problem. Only way to prevent this is to say that this m square is actually 0, because then the term doesn't exist, so even if this transforms, I don't care. So this implies that this n squared term is not invariant, so not invariant under one. That implies that n squared should be equal to 0. So for our gauge symmetry to be valid, the mass of the gauge boson has to be equal to 0. This is exactly the same argument that is used to show that the mass of photon has to be 0. Okay, photon has to be massless because the photon also obeys this U1 represent gauge symmetry. So dU therefore will have no mass, and now that it's a particle, it is going to be a kinetic. Now, here also one has to be a bit careful. Okay, so now we have to look at kinetic term for dU. You know what a kinetic term normally looks like? Actually, it should look like del mu VU derivative times derivative. Now remember that kinetic term is also part of diagram. So that should also be invariant under all these gauge transforms. If you try putting this term, you can imagine that if I replace this B by B minus some G by 2 base alpha, you will get some complicated mess. So this kind of term will not be invariant under this gauge transform. Does this mean that you can't have kinetic term? This is not true because they are bosons, so they should have some kinetic term. So you want some terms that involve derivatives. So what is kinetic term? Something that involves derivatives and two derivatives for bosons and should be invariant under this gauge transformation. So dU will equal dU minus G prime by 2 this is required. So the way to do this is do some kind of cancellation. Some terms come from with plus sign, some come minus sign, and so on. So it turns out that if you write another term which is B mu u, which is like the F mu Newton. So this B mu u is just L mu B u minus L mu B u. Then if you write down B mu u times B mu u, this term is gauge mu. This you can change by writing these. So one thing is, of course, you can check that this is involves two derivatives because B mu u has one derivative, okay, either this or this, and the second B mu u has second derivative. So just two derivatives, so it looks like kinetic term for two terms. Okay. And see, because there are many cancellations, so this is going to be like del u B u minus del u times if you apply transformations on P, it will turn out that all these extra terms actually will come with different signs and will cancel. So this you can check on this. So therefore, the net result is that if you use all these transformations, then we can introduce consistently this U1 gate symmetry. When we do that, the Lagrangian looks basically like this. The red terms are the new terms. So what has happened? All I have done is add the kinetic term for the gauge bosons, du and mu. And then we saw that the derivative just goes from del mu to del mu plus I g prime by 2 times e. Yes, all the derivatives earlier have simply gone to del mu minus something. But I can make it more specific because I know what is the y values of things and so on. So I can only look at this Lagrangian and then say that I have introduced the weak hypercharge of the. That's all it does. So this tells you that this B boson, it interacts with this L as L prime BL. It interacts with R as R prime PR. And it interacts with phi as so if you look at this term, it's phi BB term. Square. So fine, this is how we introduce U1. So if U1 is clear, I'm going to introduce SU2 by analogy. So therefore it's important that U1 should become completely clear. All we have to do is analyze this to SU2. Right, so we change it by from only del mu to adding this additional terms. See, the additional terms actually give you interactions of the gauge field with the particle. So we add this term L. You got that you have a term that combines L bar, B, mu and L. So all that has happened because of changing of kinetic term is to tell you that you have an extra interaction. So two pictures are same. See, either you can say I change my kinetic term, then it goes to something else. Or you can say that I introduce extra interaction. Right? I have my gauge goes on B and there is an LLB kind of interaction. So both of these are equivalent statements. If you write in this form, it is very clear that it is invariant. So you don't have to worry about checking all the time. So this structure is forced on you. So once you tell me that you obey U1 by symmetry, then this is forced on you. It has to be there. Actually tells you that this L bar BL vertex has to be there. You have no other choice. Also, that has to have a strength of G prime by 2 times gamma mu. You have no other choice. So gauge symmetry actually forces on you what your coupling constant should be. So different things have a different coupling constant. So now we try to add the weak isosp, SU2. It's slightly complicated because U1y simplified that you multiply by your phase. So you had a particle, so field, the particle, and you apply the standard multiplied by phase. SU2 does not act on the particle. SU2 acts on a doublet. So it is actually like multiplying a doublet to vector by a matrix. So earlier you were multiplying a single wave function by a phase. Now you are going to multiply a pair of wave functions by matrix. The way it is parameterized therefore is like this. So this 3 by 3, this 2 by 2 matrix. No, it has to be Hermitian. E power I times some Hermitian. You want to change probability. A Hermitian matrix can usually be written in terms of identity matrix plus sigma matrix. So if I have a 2 by 2 Hermitian matrix, can always write it as some A0 times identity matrix plus, yeah, so that A vector or this is SU3 transformations, SU2 transformations are transformations that take place due to this. So we are not changing the trace of the matrix. And changing trace, it would be change the probability. So what happens now? So this means that this psi x should look like a doublet. So what does this SU transformation? Where psi x is a doublet, so this is psi 1 x, psi 2 x. This should be multiplied by matrix, and if one does that, Lagrangian should stay equal. So what is this matrix? So SU2 tells you that this matrix, let me make it first. This is G by 2 alpha dot tau. So this is G by 2 is a constant, alpha dot tau. So you can see what alpha dot tau is essentially any traceless solution. If you have traced, then you come as A0 times. Now, right now, for those of you who are not familiar with group theory, you can just take it as a given that SU2 transformation means that you multiply this psi 1 psi 2 x by this matrix. Or I G by 2. So taus are so-called generators of SU. Alpha can be any vector, and it's a vector that you can choose at each space-time point separately. So alpha of x just like this is just a simple generalization. See, earlier for u1 we had e to the power I g prime by 2, and we had alpha which was a function, and instead of tau we had y. So particles were eigenstates of y. Now our particles are eigenstates of tau. So like tau, of course you can't have eigenstates of tau 1, tau 2, that is simultaneous thing, but say tau 3. Tau 3 is what we call as weak isospin. So when we say U has U is up type form, okay, and D is down type form. So we say U and D form a pair. It basically means that weak isospin of U is plus half and D is minus half. Whether we have a pair, these two have different values of G3. The isospin is equal to half, and the isospin Z component is plus half and minus half. So now what happens? So mathematical language, SU2 has 3 generators, and therefore your alpha now is 3 different vectors. You can have, so this alpha bar is basically alpha 1, alpha 2, alpha 3. Now it's 2 cross 2. Trace this. Alpha 1 are numbers. They're simply numbers. Now, earlier, since you wanted to keep Lagrangian invariant, it was easy for us to do it because there was only one phase change. Now there are, in some sense, 3 independent phase changes. And you don't want Lagrangian to change even if you apply all these 3 changes independently. So, first change is alpha 1, alpha 2, alpha 3. Therefore, to satisfy this, we can't do with just one gauge bosons, but we need 3 gauge bosons. So only B mu is not enough. You need 3 gauge bosons. W1, W2, W3. That's what is made by this transformation. So your del mu therefore should change by W mu dot tau, which is like W mu1 times tau 1 plus W mu2 times tau 2 plus W mu3 times tau 3. you need even more terms. But this is a compact of writing it, and just like our gauge field BU had to undergo transformation, the gauge transformation. So BU will be BU minus G by 2 times L alpha. All these three W2s, so WB1, WB2, WB3, have to change under transformation as this. So WB1 is G by 2 times W times alpha 1 and so on. So you can look at SU2 just like three different U1s in certain. So to get satisfy these three constraints of our three main constraints. So right now at this point you can take it from me that if you apply these transformations, these three, then Lagrange will be very clear. So this you can just take it from me if you want. Again, each of our particles are going to be eigenstates of this T3, okay, which is the weak Isosp. And these values are more intuitive because we know of things as doublets and singlets. So whenever you have doublets, like electron and electron from a doublet, so mu En has plus half and En has minus half. Up quark has plus half, down quark has minus half. And Higgs is 5 plus 5 0. So 5 plus has plus half, 5 0 and minus. So here are our doublets, right? Our doublets were electron doublet, electron and neutrino left-handed, up and down to left-handed, and Higgs, which is 5 plus 5. So for these three, the values of T3 is plus half or minus half. For all other particles, for example, all right-handed value of T3 is 0.
How do you get which is plus or which is minus? You break symmetry and then
You see how we
match it with whatever.
You match the experiment. So what is plus half, what is minus half, or what is y charge or something, finally you will the experiment. You always try to fit it into something.
In the earlier side, I was want to ask this, how do you get the y values of the
Experiments. So all these values are obtained by experiment. So for example, if you introduce a new particle, okay, what are its values of y at SU12?
But
You don't know.
but they haven't discovered X yet.
Yeah, so only Higgs of a particular kind will help you. So I'll tell you why. We may not reach that part today, but we'll reach that tomorrow. Only a particular Higgs gives a simple solution of this particular symmetry. Yeah. So right now, yeah, in some sense, since you haven't seen the Higgs, you don't know what properties will have. Okay. But then you have some good cases. We will see. Okay. So that's the way things are. So similarly, with the U1 gauge symmetry, you will get two main features. One is that this gauge bosons W1, W2, W3 cannot have a mass. So again, if you write a mass term of L square WW at the end, and if you apply these transformations, you will find that you cannot keep the energy in the end. So next thing is that you have a kinetic term that will look again like this. However, there is a slight difference. The kinetic term now is not of a simple form like we had earlier. Kinetic term. No. The problem with this now is that SU2 is not an abelian. So if it's abelian, things are easy because you can swap things. SU2 is not abelian, therefore if you only write a term W mu as del mu W mu minus del mu W, and then if you try to see whether W mu dot W mu, if it is invariant, the answer will be that it's not invariant. So you have to do something to it. In some sense, it's a subtract and error thing. What you have to do, you have to subtract a term which is G times W. What this means is the following. So, when you want to do this is a trick you have to use for all non-abelian asymmetries. Where if you want to define kinetic term, the kinetic term has to involve an extra factor which looks like minus G times W. For abelian case theories, abelian means that when you interchange things, they use this term, just say G, some epsilon I j k, W mu j. For abelian things, it means that if you interchange j and k, things should not change. An epsilon I j k would mean that. So again, this is something that I expect that either we have done this particular physics course or we should do it independently. Not spend time to this particular. But take it from me at this moment, if you don't know already, that if you define W meaning like this, then this is invariant under this rule. So then therefore, analytic term can be W mu W. A factor 1/4 in front comes because you want to transform it to something like half in this square. So that's what you have to do when you go to SU2. So exactly the changes that we got by for U1 have another changes that we want to do this one. Algebra is much more complicated. The principle is the same, but we can actually go ahead and. So now what has happened? Now that we added our SU2L, we have added all these red terms. So this is the kinetic term that we got added, WW. This is a term which is W mu dot tau, okay, which was the change of derivative. Note that R does not have this term. Why does it have this term?
That is 0 for doublet for doublet.
So for all doublets, tau is equal to 0. T3 is 0. Okay. So therefore, this term won't appear at all. And for Higgs, again this term.
It is abelian also. So it is an equal.
So you want to know this. So therefore, now that we know how Lagrange is constructed, now not referring to a book, we should be able to write Lagrange down these steps. How we do is first write down the analytic terms of from here, add U1. U1 means you add these dy terms. Then you add SU, and you add this analytic term for B. Then you add SU2, which means you add this W terms, and you add this analytic term for W, and that's it. So this part of Lagrange is no problem. So this is the so-called gauge part of the Lagrange system. So what we are going to do later on, we won't do it today, we will do it next time, is now to see how we can add terms to this Lagrangian which can give masses to different particles. So right now, among all these particles, none of them have masses. The fermions are massless. N and R have no mass terms. 5 can have a mass term 2D. So Higgs can have a mass. I haven't told you about D. Okay? But all the N's and all the R's don't have mass term. W's and V's don't have mass term. So at this point, only thing which has a mass is the Higgs boson. And all fermions and all gauge bosons are massless. And it is required for the standard model that this is the case. Because you don't want to break SU2 and U1 symmetries. If you break the Lagrangian, see, because you have symmetry, you have a constraint about what are the terms you can write. Okay. Then you can constrain those terms. Once you throw away the symmetry, then there is nothing binding, and then you get everything else. It also turns out that because we have this gauge symmetry, U1 and SU2 obeyed exactly, that standard model is so-called zero margin. There are no quantum corrections which ruin everything. Which means it makes it predictable. Because SU2 and U1 are good symmetries of standard model Lagrangian, that the standard model is predictive. And you want to not be predictive. You don't want to have random. If these gauge symmetries were not obeyed, when you calculate higher order loop corrections, every time you produce one more loop, you will produce one more parameter. And since you can in principle put infinite number of loops, this means the model is going to infinite number of parameters, which is again something you don't want. You want things to be calculable only with small number of parameters which appear in this. For that, it is imperative that SU2 and U1 are okay. Therefore, this part of Lagrangian is something that cannot be touched. In fact, even when you look at extensions tomorrow, you will also keep in mind that you will not disturb any of these symmetries. They are almost sacrosanct. So whatever you do not touch SU2 cross U1 in the Lagrangian. No one will do that. It's almost right. So I'll stop at this point of time. And tomorrow we will see how, because after all, this does not give masses to anything. But we know that all our blocks have masses. All the blocks have masses. W's and Z's have masses. So somehow we should be able to give masses to these particles without having to break the symmetry. We saw that if you give masses to gauge bosons, you break the symmetry. So you want to achieve both these things, give masses to bosons and not break the symmetry. So you have to find some way. So that is what we will see.